Okay, let's get started. A few words about the final project. Hopefully all of you have come up with something you'd like to work on between now and the end of the semester. And you described that for us and submitted it to Blackboard last night. Yes? Great. Okay, so now you're working on weekly report number 2, which is next Monday you're going to demonstrate to us with a couple of screenshots or a short video that you've implemented one step towards your final project, right? So just a reminder, what we're looking for in a final project is not an overly ambitious project, but something that seems reasonable for the 4 weeks that we have left in the semester, and that you've also thought about how to break this down into 3 or 4 weekly pieces and how to implement them as you go. Again, as I mentioned before, it's okay if along the way you realize what you had said back in weekly report 1 maybe wasn't reasonable and you come up with a modification, as long as you explain it to us. So next week, if you submit a report, you might say, my plan for this week was so-and-so, as I said in weekly report 1, but after playing around with PyroSim, I realized there was a different way to do this. I've modified my plan for this week. This is my plan in 1 or 2 sentences, and here's a screenshot or a short video that demonstrates I've implemented that piece of functionality. Make sense? Any questions about final projects? Okay, as promised, I will do a little bit of PyroSim tips and tricks at the beginning of each lecture. We talked about DT last time, which was the step size, so describing about how to make your simulation more accurate. As you start to build more complex robots or more complex environments, you might have to turn down DT or turn down the step size to make your simulation a little bit more accurate. Something else that might be useful to you, if you go to the PyroSim documentation, and just as a reminder, at the top of the final project document, I put a link to the full PyroSim documentation. One thing that might be useful to a lot of you is connecting an object to the world. So up till now, we've been using joints that connect pairs of objects together, but you can also connect an object to the world like you see in the double pendulum example down here. You'll notice a normal hinge joint at the elbow and the wrist, so to speak, of the double pendulum, but the shoulder is attached to the world itself. And the way to do that is in this little piece of code that you can see here. Here is a special kind of joint called a world joint. It is still a hinge joint as you see, but the first body is pyrosim.simulator.world. So basically you're saying I want to connect cylinder 1, which is the second object. I want to attach cylinder 1 to the world itself. Okay? So for those of you that are making robot arms, if you're making a set of stairs and you want the stairs to be immobile, you can connect each piece of the stair to the world. Okay, so you're referencing then the world rather than an object, but you're still creating a hinge joint, so we've got something that rotates relative to the world. Down here in full simulator documentation, if you search in here for fixed, there is an additional kind of joint here, which is a fixed joint, and this will glue pairs of objects together so their relative positions and orientations stay the same. This is also useful. Finally, you can create a fixed joint which will nail one body to the world. So actually, if you want to make stairs or you want to make immobile objects, the best way to do it is to connect each immobile object to the world using a fixed joint. Make sense? Okay, just some other things that might be useful to you. Okay, so back to lecture. We're going to finish lecture 22 now, which is again an attempt to try and invite the crowd, invite the world via the internet to help us evolve robots. In the Twitch Plays Robotics project, we looked at scaling up evolutionary robotics to the world by inviting people in and allowing them to issue fitness functions to the robots. In the DotBot project, we're inviting the world in to design bodies of robots and then have an evolutionary algorithm design controllers for those bodies. Why would we have people do that? Why would we have non-roboticists do that?
People have intuition.
People have intuitions about good body plans that enable locomotion through the world, right? Because we are them, and we have lots of experience watching animals move through the world. Okay. So that's the idea behind the DotBot project, that people have intuitions about biomechanics and animals that we can apply to robots, although they might not be aware that they have it. So the trick is, how do we draw that out without them explicitly being aware of it? Okay, so the first attempt to do that, as you saw last time, is to have people design the bodies, right, which are in gray here, and then computers designing controllers for them. And remember, these were very simple controllers that were just rotating the bars that make up these various DotBots. So this was the combined human-machine team. Humans make bodies, machines make controllers. We saw a purely machine team, which is in red here, which did much worse than the red team, which is people and machines working together, right? Okay, so people definitely do have an intuition about how to do this, but we would like to try and now move away from crowdsourcing, which is get a whole bunch of people to make robot bodies, to crowd seeding, which is, can we actually get machines now on top of this process to figure out what are these intuitions? Can they distill out from all the human-created designs what those features are and inject them into the machine team so that the machine team is now going to bias search towards robot bodies that have features that the crowd found useful. We mentioned two of those features last time. What were they? There were two features in the human-designed robots that were pretty obvious once you know what to look for.
Symmetry.
Symmetry. And? Simplicity, right? In a way, sort of the number of components. So actually down here, all of the machine team designs are also one component. So a component is just a set of connected bars. You can't see it in this picture, but the humans tended to create machines that had one component more often than the machine team did, right? Okay. So we ended last time by thinking about a multi-objective optimization algorithm where fitness component 1 is distance as usual, and fitness component 2 is the amount of symmetry in a design divided by the number of components. So we now had an evolutionary algorithm, which is shown in red here, which is trying to optimize F1 and F2, right? Maximize D and maximize S, the amount of symmetry in this design, and minimize C, the number of components. So manually, we went in and looked at all of these human designs and saw a lot of symmetry and few components. So we distilled out manually this feature, and then we added it as a second fitness objective in a multi-objective optimization process. So that's stage 2, crowd seeding. I'm going to show you now, to finish things off, stage 3, where we're going to get machines to find F2. So we saw, as investigators, we saw symmetry, we saw number of components. Are there other features in the human designs that we may have missed? And it's hard to tell by looking at these simple designs, but it turns out that there are. How did we do this? Well, the first thing we did is to treat our DotBots as graphs. Graphs are just a set of nodes connected by edges, and there's a large field in mathematics about studying graphs, and there are a large number of metrics you can come up for describing graphs. So for example, let's see here, let's pick one. We already talked about number of connected components. That one's pretty obvious. Symmetry is in there already. Degree is mentioned here several times. So degree is the number of edges that are arriving at a node. So if we have a given node in a DotBot, we might look to see what is the single node. What is the single node that has the largest number of edges arriving at it? Or alternatively, for exactly the same DotBot, we might ask, what is the node that has the fewest number of edges arriving at it? So each element in this list here is some descriptor of a single graph, right? So there's many more things we could imagine aside from symmetry and number of connected components. And the question then becomes, is there some combination of these features that best captures features that exist in the human designs? And how would we ever go about finding such a set of combinations? Yes?
Multivariate statistics.
What's that?
Multivariate statistics.
Multivariate statistics. I'm going to show you one way to do that. There are many ways we could do that. So the way we're going to do this here is to use, as always in this class, an evolutionary algorithm. Okay? And you might remember when we were talking about evolutionary algorithms back in lecture 4 or 5, we mentioned genetic programming. What distinguishes genetic programming from the other evolutionary algorithms we've talked about in this class so far?
Genetic programming, instead of putting in weights, you put in functions.
We put in functions, exactly. So we're going to be evolving combinations of functions that try and describe the set of human designs. And we're going to encode these functions as trees. So in genetic programming, the genotype is a tree that encodes a function. And in genetic algorithms and all the other evolutionary algorithms you've seen, it's usually a vector or some other data structure, right? Okay, so let's create a single tree. Let's pick one of these elements at random. Let's say, let's do maximum degree. We were just talking about that one. So I'm going to create a tree that has a single node in it. And in that node, I'm going to put dmax. And I'm now going to do what I just did before. I'm going to do a multi-objective optimization process here where I have distance on one objective. And before, I had S over C here. So I'm going to, this was the one that we came up with. Let's try this one. So now I'm going to put dmax over here. And I'm now going to draw a whole bunch of dots. And each dot here corresponds to one of the robots created by the original human-machine team. So each one of those designs has a distance. Someone clicked, or a group of people clicked go a whole bunch of times on one robot design. And for that robot design, a controller was found that got that robot to travel this distance. Another robot traveled this distance, another one this one, and so on. And what we're looking for now is there a relationship between dmax. If we look at the actual design of each of these d-bots, they each have their own dmax here, and distance. Question?
Sorry, what was dmax again?
So dmax up here is maximum degree. So let's say we have, let's draw an actual dot bot here. Okay, I'll just make one at random here. Okay. Here's a dot bot, and we're gonna calculate for this dot bot its distance that was traveled. Let's say this was a human design. Let's say this particular dot bot traveled this far. Okay, now what is dmax? Well, we visit each node and ask what is the degree at that node. So the degree here is 1. We have one edge arriving here. The degree of this node is 1. The degree of this node is 1. The degree of this node is 1. The degree of this node is 3. And we're looking for we have 3 edges arriving at this node.
Isn't the second one 2?
The second one, did I miss one here? 1, 2, 3.
You started.
Sorry, thank you. This one, second one. Yes, this has a degree of 2, 1, 1, 1, and 3. So of all the degrees that exist in this one design, the max degree is 3. So let's imagine this corresponds to 3 here. So we're taking each design and going into our data set from the human trials and saying how far did that robot travel, its distance, and what was its dmax. Okay? And this is all for one tree, one guess by the computer about a feature that might predict or explain how well the designs did. So how close is the relationship between dmax and d in this picture? Zippo, right? There is no good relationship between dmax and d. So this gets a low fitness. So the fitness of any one tree in the genetic programming algorithm we're about to run is how close a relationship it finds between the tree, which describes combinations of features, and how well they did, right? So what this evolutionary algorithm is doing is searching over the space of all descriptors of the dotbots, and it's looking for one that captures what the crowd was actually doing, right? If we grabbed a random user on the dotbot project and said, hey, you created a great dotbot design. Why did you create that design? It's unlikely that they're going to tell us, well, I was trying to create a robot that had a maximum degree of about 3 divided by average clustering raised to the average degree connectivity, because clearly that's what makes for a good locomoting animal and probably makes for a good locomoting dotbot, right? Someone might, if they were paying attention, tell you in retrospect, now that I think about it, I was tending to make symmetric designs. They might be able to tell you that. They might be able to tell you, if we look at number of connected components, they might say, I realized that you could make 2 or 3 little bots in the dotbot interface, but I figured I should probably make like one big one. That was probably going to do better than a lot of small ones. So they might have a little bit of intuition about S and C. The question is, are there other things going on that they might not be aware of that they can't tell you? So this whole process here is an attempt to see if we can automatically distill those intuitions out of the crowd. That's the idea. Question?
Yeah, so did you say that this is searching for like combinations of these variables too? So
it's going to
raise to the top. Okay.
Exactly, not just individual elements, right? So there are how many elements here? About 11 of them. So you can imagine we do what I just did here 10 more times with each of these and look to see how close the relationship is. But as we already know, it's not just S and it's not just C, it's S divided by C, which tends to be a little bit better descriptor of what the crowd is doing. So we're going to look at combinations of these features as well, which we'll see in a moment.
I was also wondering if people chose sort of a shape that looks similar to an animal, because that's what.
So you'll notice here we created one feature number of limbs. So what is a limb in a dotbot? It's any edge that has, it's any node that has a degree of 1. So we counted limbs as sort of things that were hanging off the side of the main thing. So perhaps, where is it there? Number of limbs, L equals 4 might be a good descriptor of what people were doing. Maybe people were building quadrupeds or trying to build them in the dotbot interface. Maybe. Right? That's a hypothesis, and we're going to try and automate this whole process. So far, so good? Okay, so I showed you one tree here, which was just a single feature. So we're going to play this game all over again. This was just one tree, and remember in genetic programming, we have a whole population of trees. And where do these trees come from? Well, in the initial population, as always in an evolutionary algorithm, we start with a population of random trees. So we have our variables over here, and on the right we have a whole bunch of operators, which are ways of combining these features together. So let's build a second tree at random. I'm going to flip a coin. Heads I'm going to pull from the bag of variables. Tails I'm going to pull from the bag of functions. I flip a coin, it comes up tails. I reach into my bag of functions, and I roll a 14-sided die there, and it comes up 1. Which means I pick addition. So I'm randomly picking one of these 14 functions. And let's say I pick plus by chance. Plus has 2 arguments associated with it. I have to add 2 things together. So I now have a root node of my tree, and I now need to fill these 2 empty nodes. So I flip a coin again. Heads, I'm going to put a variable in here. Tails, I'm going to put a function. Let's say I flip a coin and it's heads, reach into the variable bag, and by chance I pull out G, and flip a coin again, and because I'm getting tired, let's put L in here. So here's my second random tree, which becomes G plus L. right? Remember that each tree is encoding an equation, and it's an equation that's trying to describe combinations of features, right? And imagine now, when I plot distance to G plus L, I get something that looks like this. The relationship between G plus L and D is a little bit more cleaner than before, right? So the correlation is stronger. So far, so good?
A couple of questions. One,
Sure.
What is maximal matching? I'm sorry if I missed that.
I don't remember. Again, we're straying outside my area of expertise here.
And
Any
then also-
graph?
Maximal matching is like the number of edges you can pick so that they're not sharing. So matching is you match all the nodes in the graph that are covered by an edge, but the two edges can't share anything.
Okay.
So like if you had a bipartite graph that's just like two sides and it's like a ladder, you can pick all the middle, but you wouldn't want to pick something that starts from two.
Okay.
The maximal matching is the number of edges you can pick.
To do that. Okay.
It might not be a perfect matching. A perfect matching is when you do cover all the nodes.
Okay. That sounds like a pretty good description to me. Okay. So there's a large number of these, again, and we're going to see if it's not just maximal matching, but some combination with others.
Did you allow for constants?
That's a good question. I think constants were allowed in here, I think. I have to go back and look at the paper, which I think is linked into the schedule for today. Okay, so the fitness of this tree, again, is proportional to how well this description predicts how well the robot did, right? The higher this, the higher D, right? That's what we're looking for. Okay, so this survives and the other tree dies off. This tree produces some randomly modified copies of itself. We might mutate this, and this might become, for example, G plus S divided by C. We know that S divided by C is already somewhat predictive of the distance the robots travel, right? But maybe there are additional things like G which also help with predicting that. So we're now running this evolutionary algorithm that is searching over the space of all possible functions, and the fitness of a function is how well it describes the designs, the good designs produced by our human users. Okay, so we run this process, we run this process, we run this process, and we got back several trees that were much more predictive of performance than just S over C. So it turns out that whatever people were doing, whatever intuitions they were drawing on, it wasn't just S, it wasn't just C, it wasn't just S divided by C, it was other things that could be described as combinations of these. Anybody have any guesses? What were we missing that the genetic programming process found? It's a tall order for 8:30 in the morning. Okay, don't feel bad if you couldn't figure it out. We couldn't either. Here are 10 trees written as equations that do way better than S divided by C. You'll notice if you look carefully that a lot of them have S and C in them somewhere. Don't ask me to describe what any one of these things actually is. Error is plotted on the right, and remember that lower error is better. So error is the difference in prediction that G plus L makes about D. So an error of 0 would be a bunch of points that lie exactly along this line. An error of 0 would mean the higher the value of this equation, the faster the robot traveled.
So is that like an extension of like R and R squared for linear regression, but for multivariables?
This is multivariate regression done using genetic programming. That's right. Multivariate nonlinear regression, because these are definitely nonlinear equations.
So these did well, because it looks like they didn't.
These did very well. We should have put S divided by C over it, but S divided by C had an error much higher than 0.8. I don't remember what it was.
Should that be over one?
It could be over 1. That's right.
okay.
Yeah, I'm sorry. I didn't go into this in too much. Yes. Okay.
Like mean square errors and like
I think so. Again, we'd have to go back and look at the paper. All I remember for now is lower error is better. And these are much better than S divided by C, which is good enough for our purposes today. Okay. So whatever people were thinking about, whatever our model is about what makes for a good dot-bot, hard to say. It's probably pretty complicated. I'm not able to articulate it when I play the dot-bot game, but there's certainly rich intuitions that people have that if we do it in the right way, we can actually pull those out of them. Okay, so now for fun, we took one of these 10, the one that had the lowest error. It was tied with this one here, but we took this one up here. And we now gave that to the computer. So I'm not going to write out equation 1 here. We'll just call it 1. Okay? And so now we threw away the genetic programming. We're done. We took the solution it found, and genetic programming said this is what people try and maximize in their designs. And when they do, then I'm able to find good controllers for those designs. So we reran our multi-objective optimization algorithm now, which was designing both the body of the dot-bot and the controller. And the fitness of any one dot-bot was how well it scored on 1. We took all of the features that described that one dot-bot produced by the computer, computed the value of that equation. We plugged in all of the features and get back a single number. So here's the actual value of equation 1 when we plugged in the features from one dot-bot. And the computer ran a few controllers on that and looked at the best controller and found the distance that it got the dot-bot to travel. And we were trying to now maximize D and maximize the value of equation 1. So in phase 1, we were just optimizing distance. Phase 2, the computers were optimizing distance and S divided by C. And in phase 3, the computers was now optimizing D and equation 1, maximizing D and maximizing the value of equation 1.
How much overfitting do you think is going on here?
Maybe some, right? That's always possible.
Max doesn't seem useful.
There may be some overfitting, but it was certainly more predictive than what we could come up with, which was S over C. And this is what we got. So now control here in red is the result from phase 2, which was D and S over C. And using equation 1, the computer could squeeze out a little bit more distance from the robots. Not a lot more, but some. Right? So what this shows is that when we, as the investigators, try and distill out features from the crowd, we can't do as good a job as the genetic programming process did. And it tells us, in addition, whatever people were doing, they had some pretty sophisticated intuitions about biomechanics, what makes for a good locomoting robot. Okay, that's phase 1, 2, and 3. This project is still ongoing. If you were to take over this project, what might you do for phase 4? Remember the overall goal of this project. We want people to help us design good robots. We're combining people together with machines.
Well, when you were describing through the day, you said one of the variations was to show the scoreboard at the top.
That's right.
Top ones that people had made. So you could show the top machine ones and then see what people do.
That's a great question. So let's see what they actually look like. That's a good point. These are the designs that did better. These are the top 5 produced by this phase 3 process that maximize equation 1 and maximize D.
When it has multiple components, is it the distance to the closest one?
It is the, that's a good question. I think it's the, I think it's the center of the biggest component, if I remember
It's
correctly.
really small and it doesn't really matter.
It doesn't really matter too much. Okay.
I mean, they don't look just any different than the control ones.
They don't, right? Which is kind of strange.
So if you're maximizing all of these other variables and they still don't bias the search towards what humans are designing, maybe
They're clearly not biasing search towards the actual designs produced by people, but they are biasing search towards the underlying features that describe all of the human designs. So in essence, what the computer has done is said, okay, humans, you seem to have an intuition about what works, and I'm going to try and distill out that intuition, and then I'm going to follow the intuition, but I'm not necessarily going to copy the designs that you copy. So it's moving in more or less the same space of dotbots that have these underlying features, but clearly they look very different.
I wonder if those are somehow easier to control. If
They are easier to control because it was easier for the evolution, at least easier for the evolutionary algorithm to find controllers for them.
right.
So phase 4, which we're still working on, is showing people this doesn't necessarily help them. Maybe. Showing them this probably doesn't help them. Could we do something else? Could we simplify this picture? And could we simplify this picture in some way to help people understand, sort of reinforce their intuitions? Might we be able to go all the way back to the beginning and say, okay, humans, you get to design dotbots again, and here are the kinds of things that you and your peers tend to do?
I don't know, telling them if the parts of the equation, like humans that have good degree maps and
Maybe.
The connectivity is a Gaussian distribution.
Perhaps.
That definitely helps.
Perhaps. I don't know. If you have any good ideas, let us know.
You could, it would probably make it a little bit worse, but if you put like another fitness being tested of like something simple like just S or like S over C, and then maybe those bots would end up looking a little bit more like human bots, but with like some other X factor.
That's a great idea, right? So this is sort of this is when we open up the engine, right? And we allow equation 1 in its entirety to design robots for us. But maybe we take one small piece of this equation, or go back and do the genetic programming process again, but only allow it to make small trees. It's not allowed to make big, complex trees like this. So maybe with simpler features, it may produce more intuitive-looking dotbots. I don't know. We haven't done that yet. But that's a good idea.
I'd be curious about, so did you try any other less complicated multivariate analyses before going this direction?
I'm trying to remember now. This is one of my PhD students. I don't think so. I think we went straight to GP. Maybe there's something else we could do.
I'm wondering if some sort of supervised machine learning process like linear discriminant analysis would pull out linear combinations of these variables more simplistically that seem to be good predictors, maybe separate like the control, the human one, into predetermined categories, and then
Yep.
You could pull out the linear combinations that explain most of the variance and group separation and list those maybe to other humans to say, try to build robots that maximize these things.
Exactly.
Don't give them the equation to say symmetry is important according to the...
I think that's a great idea. So again, a different way to try and simplify things, right?
That's confusing, but
it's
a list of variables that
maybe, right?
pulls out might not.
So maybe if, again, we were able to come up with a crowd-friendly way of describing these, most of the variance in the designs, or the designs the crowd previously created tended to have lots of S and C and G in it. Ask people to design again and see if they can do a better job than they did the first time around.
Do you think that, like, also that equation, maybe people like do look at these things, maybe one or two of them at a time, and that's like our intuition. But we're not able to look at like 8 different things.
Exactly. Absolutely. I can't, right? There's actually, I think we'll pause this and move on in the interest of time. Just last thing I wanted to say about this is there is a now very hot field within AI, which is called explainable AI. And you can see why this is now a very popular area in AI research. These sorts of things and deep learners are now getting very, very powerful. They can become very predictive and decrease error on whatever we ask them to predict or recognize or classify. Getting very, very powerful, but becoming more and more opaque as they do so. It becomes harder and harder for people to understand them. So there's an open research question now, which isn't just in evolutionary robotics, but in the whole field of AI, which is, can you design AI which is predictive and explainable? So the machine or the model itself can not only predict, but explain to a human why it predicted what it predicted, right? And you can imagine a lot of reasons why that would be useful. Okay, again, that's just wanted to throw that out there. We could have a long discussion about explainable AI, but let's get back to evolutionary robotics. So we've just completed lecture 22 and also completed our theme on open problems in the field of evolutionary robotics. Like I just mentioned with explainable AI, there's lots of other open problems in the field, but we're going to move on. We're now going to switch into our two-part lecture on collective robotics, and the underlying question in both of these lectures is, how do we evolve robots to work together to do something that would be beyond the ability of any one robot? So in real-world robotics, so NASA's designing their next generation of robot probes. People are creating disaster site robots to search for human survivors. Any robots that we want to deploy in the real world, there is always a question up front, which is, do we make one complex machine? Do we make a few medium complexity machines, or do we make a large number of small, simple machines? So obviously it's a continuum, and how do we make a choice along that continuum? That's what we're going to explore from an evolutionary robotics perspective. Okay, so let's start with lecture 23 here on swarms. And as always in evolutionary robotics, we're going to start by taking our inspiration from nature. Animals swarm, fishes school, and birds flock. Most animal species are pretty good about working together. Humans, so-so. Anybody know what these particular birds are?
Starlings.
These are starlings, right? So if you Google starlings, there's some beautiful videos of flocking. What if you were a starling in this flock, what are you doing? What are you thinking? First of all, don't hit anyone, right?
Yeah, big don't hit anyone. Just trying to stay like within a certain bounds of distance away from your friends, and trying to make sure that you end up having similar wing shape, and so that you're going in generally the same direction and the same velocity.
That's it, right? So generally keep a certain distance from your neighbors, head in sort of the same direction. If you're an average member of the flock, you're probably doing something like that. What about the leader? Which starling here is saying, okay guys, let's go this way, let's go that way?
There is no leader.
There is no leader, right? So again, thinking about thinking is misleading. So in a lot of robot swarm projects, people create 10 robots and say, okay, this one is the leader and it's going to send out a signal to the other 9 about what direction to head in, which works fine for 10 robots, doesn't work so well for 100 robots, certainly doesn't work for 10,000, and clearly doesn't work for however many starlings are in this video. So centralized command doesn't scale up very well. And remember, one of our goals is to scale up robotics. So in all the work you're going to see here, we're going to abandon centralized control. There is going to be no one robot leader. There's going to be this sort of flat coordination, which is hard for people to think about. If you want to try and design a group of robots, we think like humans. There's going to be one boss, and there's going to be 5 sub-bosses and 10 sub-sub-bosses. It's hard for us to think about decentralized control. Thinking about collective thinking is misleading. Okay, so that's starlings. Let's look at what are called boids. And boids were invented back in the 1980s by a researcher in computer graphics, which took the ideas you were just mentioning about sort of maintain your position and distance relative to your peers and distilled that down into 3 simple heuristics: separation, alignment, and cohesion. So what does any one Boyd see? First of all, we're going to look at the green Boyd. So this is called the ego. So we're going to talk about one Boyd and what it sees from its point of view. It's the ego. So the ego sees, it has a sensory volume. So this is usually done in 3 dimensions. So there's a sphere around each ego, and that's the boundary of its sensation. So whichever of its neighbors are inside that sphere, it can see each of those neighbors. It knows the relative position of that neighbor. Is that neighbor to the left and down and behind me? Is it to the right and up and a little bit in front of me? It knows its relative 3-dimensional position to itself, and it also knows the heading of its peers. Okay, so first of all, separation. So if there are too many neighbors, if I'm crowded, I should try and move a little bit away from them. So it computes the positions of, in the top picture here, it's 3 peers, and finds, it computes the vectors that connect itself, the ego, with all of the neighbors, and sums up all of those vectors. And if they're unbalanced, meaning there's more of your peers on one side or the other, if that sum is non-zero, the ego will turn its heading a little bit towards the red arrow, which is the sum of all of those vectors, right? So if I'm crowded to the left, turn a little bit to the right. If I'm crowded from below, move a little bit up, and so on, right? Okay, that's one little heuristic. Second little heuristic is alignment. So I know the ego knows its own heading, and it knows the average heading of all of its peers within the sphere of its sensation. And it takes the difference between its own heading, shown with the green line here, and the average heading shown by the blue one, and changes its heading to match a little bit closer to the average heading. So align the direction you're traveling in a little bit with your neighbors. Last one, cohesion, is sort of the inverse of separation. Take the positions of all of your neighbors and find the center of mass, or the center of position. What's the average position of all the neighbors? Forget about yourself for a moment. And then align your heading of the ego, align the ego's heading a little bit towards that central position, that average position. Okay, those are 3 different heuristics. At every time step in a Boyd simulation, and I'll show you a Boyd simulation in a moment, at every time step, each individual in the flock is going to run exactly the same algorithm. It's going to compute each of these 3. And each of these 3 outputs a change in heading, right? 3 changes of heading. Sum up those 3 changes of heading, which gives you 1 change of heading, and the Boyd updates its heading accordingly, right? So we have a whole bunch of individuals in the flock, but they're all running exactly the same piece of code. Okay. So the Boyds were invented back in the 1980s when computer graphics was just getting going, so apologies for the quality of the video. This was state-of-the-art back then. Hopefully you can see this video a little. You can see this video okay. We've got our voids moving through 3-dimensional space. They flow around objects. And when they get to the far side of an object, they recohere into a swarm, right? Pretty amazing for the time. Okay. So the question that I haven't answered yet is, how do they sum up these 3 terms? Usually we do it with equal weighting. What would happen if you weighted some of these terms more than others? What would happen if we weighted separation more than alignment and cohesion? What if you reran the same simulation you just saw, but now separation has more of an influence on change of heading than alignment and cohesion does? What would the swarm do?
Less dense.
Less dense, right? It would become larger and less dense, but it would still more or less align and cohere. If cohesion was weighted more than the other 2, you would get a much more smaller, tighter, denser swarm. What happens if alignment is weighted more than the other two?
Circles.
Maybe.
Well, it wouldn't change direction very much. Like, it'd be hard to steer a ship if you're like, oh, my friend moved, but I have to move with him.
Possibly, right? It depends on what your friends are doing. So you might actually get something that's very chaotic or going around and around. If your neighbors are more or less by chance happening to head in the right direction, all of your alignments might converge to the same, and you might get a bunch of voids that fly off into the sunset. It's hard to say. One of the interesting things about coding up collective swarms is it's hard to predict beforehand for a set of rules how the swarm is going to behave. Again, we've moved into yet another territory that's very non-intuitive, which means, as you can guess, we're going to apply evolutionary algorithms here. So no evolutionary algorithms so far. We're hand designing, or Craig Reynolds, who originally came up with these in the 1980s, came up with these rules. Are there other sets of rules that we could design for swarms to get them to do other things?
So this makes a lot of sense in terms of the just changing the direction.
Yep.
For fish, which is like right next to it.
Yep.
But I would think for something three-dimensional, it would have like more, like birds can do more than just change their direction clearly, and like maybe one of these traits would be maybe like separation usually involves just speeding up and occasional like a sharp change in direction, whereas the alignment and cohesion is more of like a tinkering kind of thing?
Possibly. So in here, and this is again, I'm describing the vanilla Boyd's algorithm, and there's now a gazillion variations on this. There are some where the Boyds not only change heading, but change speed, acceleration, all sorts of things, right? That's a good point. Okay. All right, so a very, very simple algorithm discovered in the 1980s, very powerful. And in the 1990s, Hollywood found out about it and started to include it in movies, and The Lion King was the first debut for the Boyd's algorithm. If you watch carefully in this animation, you'll see a lot of the things you just saw in that simulation from the 1980s. Notice the wildebeest going around the spur of rock. All right, any movie you see from Hollywood these days when there's a large number of combatants or animals, there is some version of the Boyd's algorithm running at the lowest level. Again, they've become very sophisticated over time, but at heart, you have a large number of independent actors, which are all running exactly the same algorithm, but they're in slightly different micro-environments. Wildebeest I happens to be near the spur of rock at time t, and wildebeest J is only surrounded by other wildebeest. So they do different things because they have different local environments, but they're running the same code. Okay, there is nothing in this set of equations about flow around, recognize the cylinder and flow around it and meet up with your peers on the far side. There's nothing that says avoid spurs of rock or the sides of the box canyon. Why does that occur?
Well, you need another rule, or apply the separation rule to physical.
You apply the separation rule, you apply all the rules to other things. So from the ego's point of view, this thing over here might be another Boyd, or it may be a piece of rock which has a relative position relative to the ego and has a heading direction of 0. I haven't seen that thing move yet. I'm moving, but it's not moving, right? So if you write these equations in the right way, where you're agnostic to what the other things are, you get elegant side products of these algorithms, which is obstacle avoidance, recoherence of the swarm, right? Once the object has passed me on the left, suddenly I see some new peers that weren't there before, which are the peers that took the left path around the object. Okay. Okay, so we're going to take some of these ideas and move them into the present in robotics, and we're going to continue looking at this theme of predator and prey. And I promise that no animals were harmed during the taping of this lecture. These are all going to be virtual lions and gazelles in a moment. But let's talk about real lions and gazelles for a moment. When we talked about legged locomotion, one of the chapters had this particular figure in it, which is showing the speed curves for lions and gazelle. If you were a lion and your favorite meal was gazelle, what would you be doing out on the Serengeti plain? Obviously chasing gazelle, but how would you be chasing gazelle?
By ambush.
By ambush, right? If you have a cat at home and it gets very low and very slinky, this is the reason why, right? So cats, large and small, tend to have higher acceleration curves than most prey species. So you better get pretty close and accelerate very quickly. And if you do, you've got less than 4 seconds to catch the prey. If the lion doesn't catch the gazelle within 4 seconds, working on its own, it's never going to catch the gazelle. So big cats and a lot of other species realize, well, I don't necessarily need to work alone, right? If I can hunt in packs, I can start to change the balance of power here, right? So one predator against one prey usually doesn't work. So predators figured out how to work in packs, which of course exerted selection pressure on prey species to also move in a coordinated fashion. And you got an evolutionary arms race between prey species and predator species, which over time become better and better able to coordinate their actions. They evolved coordination strategies. So that's exactly what we're going to look at now. So we're going to go from the real Serengeti plain to the virtual Serengeti plain, where we're going to ask, can we use evolutionary algorithms to evolve behaviors for teams of virtual predators? And if so, what does that evolutionary algorithm look like? How are we going to do it? And if we're able to do it, like we just saw here, what kinds of solutions does evolutionary algorithms come up with? We don't know exactly what's going on in the heads of lions and groups of prey when they try and catch or evade the opposing number, right? But we can, if we do this with virtual lions and gazelles, open them up and see what sorts of coordination strategies evolved. Okay, so here's our virtual Serengeti plain. It's a two-dimensional plane. It's going to be very simple. No physics engine here. We're just going to place one gazelle G in this two-dimensional plane and 4 Ls. We're going to have 4 lions, and the 4 lions are going to chase the gazelle. The gazelle is going to move 3 times faster than the lion, so we're going to make things really hard on the predators here. So at every time step, the gazelle is going to update its position, and we're going to visualize this with vectors, so you can see where G is going to end up at the next time step, and you can see where each of the 4 lions is going to end up at the next time step. So the disadvantage for the lions is speed, but the advantage for the lions is if they're able to, they can coordinate their behavior to capture the gazelle. Okay, this virtual Serengeti plain or the savanna is toroidal. What does that mean? Well, imagine that our 2D plane here is a sheet of paper, and I fold over the sheet of paper so that the 2 long edges of the piece of paper are touching one another. I have a tube. And then imagine I take that tube and turn it around so that the 2 ends are touching, and I now have a donut. So from the point of view of our gazelles and lions, they're running on an infinite 2-dimensional plane. But from our point of view, it's a toroid, it's a donut. Okay, so again, it's hard to draw that. So I'm going to keep drawing things on this 2-dimensional plane. And remember, it's infinite. So the gazelle at time t, it wants to move up and to the left, which would take it off the edge of the sheet of paper. But remember that that top long edge is connected to the bottom long edge. So it's going to wrap around, and the gazelle is going to end up at this position at time step t plus 1, right? So the gazelle and the lions can run forever without ever reaching the edge of the virtual Serengeti plain. Likewise, the lions can sense the position of the gazelle. So in this picture, it looks like L4 is a long way from GT plus 1, but L4 is actually close to GT plus 1 on the toroid. Just keep that in mind. Okay. Okay, we're going to hand code the behavior of the gazelle, which you see on the right here, and we're just going to evolve the behavior for the predators. So what does the gazelle do? The gazelle is going to sum up a bunch of vectors. So we're going to create a set of vectors, uppercase V, we're then going to draw out of that set of vectors smaller lowercase v, where each vector in the set corresponds to a vector that goes from the gazelle to the lion. So we have 4 vectors, like you see here. We're going to sum those vectors, and when we do, when we sum them, we're going to divide each of the 4 vectors by its magnitude. This term over here is just to normalize this sum, so you can sort of forget this term for a moment and just focus on this. So we're summing up a weighted sum and then taking the negative of that vector. Okay, why are we summing up a weighted sum? Remember, this is we're computing the vector along which the gazelle is going to move at the next time step.
You want to move farther away from the ones that are the closest.
Exactly. So the ones that have, the vectors that have small magnitude, those represent lions that are close to the gazelle. So when you sum up these vectors, the resulting summed vector should be more influenced by the smaller vectors than the larger vectors. And then why do we invert the vector? Why take the negative?
So shorter distances will count as factor greater into its fitness.
Not quite. So we've summed all of these vectors, and we're now going to use this summed vector to move the gazelle.
You want the inverse, you go the opposite direction.
Go in the opposite direction. If we don't take the negative sign, the gazelle is going to run towards the closest lion. Not a great thing for the gazelle to do, right? So the negative sign means run in the opposite direction. Okay, so we're hand-coding the behavior for the gazelle. Sense all the predators and react most strongly to the nearer lions. Now we're going to evolve behaviors for the lions. And luckily, because we just talked about the DotBot project, we just talked about genetic programming. We're going to use genetic programming again here. There are 3 variables that we can use, and you know these are variables because they require 0 arguments. And each of these variables is a vector. The first one is 1 unit in the direction the lion went last. So I'm a lion, and if I use last variable, that means what is the direction I traveled in at the last time step. Random direction, a random vector on the toroid, and gazelle is the smallest vector that connects me to the gazelle. Why the smallest? Well, remember that because we're on this toroidal plane, there's lots of vectors that could connect me with the gazelle, and take the shortest one. Question?
I'm just wondering why, where the what the random vector is normal to.
Random normal vector. I think that means of length 1. I think.
Unit vector.
I think they meant unit vector. I think that's what they mean.
Okay.
Even scientists make stupid mistakes. I think it's unit vector. Okay, so let's make a random genetic programming tree, and the only thing in that tree is 1 variable, which is last. So every time I execute this function, it returns not a number but a vector, which is the vector the lion traveled in at the last time step. Let's say I take that 1-node tree and I drop it into each of the 4 lions. We know what the gazelle is going to do, and we turn on the simulation. What happens? We turn on the simulation, so it's just started.
Does it just, well, if it hasn't moved at all, it might not move, but if it does move somewhere, then it will only
It'll
go
just
one
keep
direction.
moving in the same direction it traveled in at the last time step. So we're not quite sure what happens at the first time step. Naively, I would think they didn't move, so they probably just don't move at all. Is that a good strategy for the lions? Probably not going to catch the gazelle. Conserving energy, that's true. That's true. Okay, what about, let's make a second tree at random. RD, which is random direction. Restart the simulation. What do the lions do now? All 4 of them move at random. How good a job do they do at catching the gazelle? Not very good, right? So we've just made 2 trees at random here, which don't do a very good job at capturing the gazelle. Let's do the third one here, G for gazelle. The lions are going to move in the direction of the gazelle. How is that simulation going to do?
Better than the other two.
What's that?
Better than the other two.
It's actually not going to do better than the other two. It's going to do even worse than the previous two. All 4 lions will move towards the gazelle, which means all the lions are moving towards one another, and the gazelle moves away from them. It's easier for the gazelle to maintain distance from closely clumped lions than it is if they're randomly moving and spread about on the plain, right? So the worst thing the lions can do in this case is run towards the gazelle. So the remaining elements in this list are vector operations. Remember that now in our tree, it's always returning vectors. So let's make another random tree. We reach into our bag here and we pull out a plus at random. Plus requires 2 arguments. Let's say at random we choose G, and at random we choose random direction. What if we took this tree and dropped it into each of our 4 lions? What does this hunting pack do? We're taking one random unit vector and adding it to the vector that connects each lion with the gazelle.
Well, it seems like they would spread out a little more.
Maybe. They'll kind of chase the gazelle, but they'll kink and jibe a little bit as they do so. Will they get a little bit closer to the gazelle? Maybe, maybe not. Hard to say. Okay, that's the idea though. And we're going to then run genetic programming and create tens of thousands of these trees. And the fitness of each tree is how close the lions get to the gazelle. Makes sense, right? Okay, you can read through the rest of this. Some of these vector operations are a little bit less obvious, but they kind of make sense when you start to think about them. There might be some combination of these vector operations that produces a successful strategy. Okay, so that's going to be experiment 1, and I will show you the results from experiment 1 at a moment. They did a large number of slightly different experiments. Experiment 2 is they added in 4 additional variables to the bag of variables. Remember, we have a bag of variables and a bag of operations. So these 4 additional variables give the lions an additional ability, which is dietetic sensing. Dietetic sensing, or dietetic, means relative to ego. It's like the Boyds. It's going to be things that are relative to me as a lion, right? So as a lion on the Serengeti Plain, I can see the gazelle, but in this case, I can't see my 3 other lions. I can see the gazelle. I know about myself. I don't know about the other 3. So these additional ones give me information about what my other 3 lions are doing. So nearest is the vector that connects from the lion that's closest to the gazelle to the gazelle. For the ego, that might be the vector that connects me to the gazelle if I happen to be the closest. If I'm not the one that's closest to the gazelle, it's a vector connecting one of my peers to the gazelle. And the lion can see, quote unquote, that vector. We can include that in these trees. Okay. Then there is lion, which is the vector that connects me to my closest neighbor lion. And then there is right lion. So I'm heading in this particular direction, and as I'm heading in this direction, I start to sweep in a clockwise manner along the plain. And the first lion that I see on my right side, that vector becomes our lion. Alternatively, as I'm traveling in this direction, I sweep counterclockwise, and the first lion that I see on my left becomes L lion. So as I'm chasing the gazelle on the plain, there may be some combination of these pieces of sensory information that, combined with other pieces of sensory information, may allow all 4 of us to coordinate our action and capture the gazelle. That's dietetic sensing. So far, so good? Okay, that's experiment 2. So experiment 2 is we throw these 4 variables into the variable bag. Experiment 3 is we take these 4 variables out of the variable bag and we throw these 4 variables into the variable bag. So in experiment 3, we're now going to do name-based sensing. So now there are 4 additional vectors that can be incorporated into the GP trees. And these are the vectors that describe the connection between lion 1 in the gazelle, lion 2 in the gazelle, and so on, right? So we're naming the lions by name. 3 different experiments. All 3 of these experiments are exactly the same. The only difference is that in these 3 different environments, the lions have slightly different perceptual abilities. Okay, given these 3, yes?
So they don't have those abilities, they have the option to evolve those.
They have the option to use them. We're not forcing them to use them, we're throwing them in there for evolution to use. And evolution can try and combine these in different ways to come up with a good hunting strategy for the pack, for the pride, right? Okay. Which of these 3 experiments, in which of these 3 experiments do you think evolution did a better job of evolving coordination strategies?
Name-based.
Why?
Allows for better coordination.
Why? Define better coordination. What is it about name-based sensing that allows better coordination? Part of the draw of doing these kinds of experiments is it forces us to be a little bit more specific about what we mean by cooperation, coordination, and as we'll see in the next lecture, signaling and language.
Yes, I would go. I would think that the second one, the dietetic sensing, would be the best.
Okay.
Name-based wouldn't really. I don't think it would really matter because it doesn't really matter if George or Sally is closer.
Maybe.
It more matters what the relative positions are.
Possibly.
Are the lines not identical? They're not identical, right?
Okay, so that's a little twist that we haven't described yet. At the moment, assume that all 4 lions have the identical strategy. They're like the Boyds. They're all running exactly the same strategy, whatever it is in their heads. Any other guesses? Okay, let's push on. So I just mentioned 3 different experiments to you. They made 3 other variations. So one of them was what we just described, cloning. So for each strategy, we're going to clone that strategy in the heads of the 4 lions, right? They all have identical strategies. In the next experiment, free breeding, we're going to create one big tree, which has an empty root node, and it has 4 subtrees. Each of the 4 subtrees is the strategy for one of the 4 lions. So imagine now you have a genetic programming experiment in which you have a population of these things, where each individual in the population, if you pull it out and you then unplug the 4 subtrees, has specific strategies for each of the lions. So now they can do different things, or they can use different strategies. How do we evolve these things? Well, one way is to take 3 individuals in the population, for example, in this case, and we copy subtrees into the new child. So here we have 3 parents producing 1 child strategy, and we take the strategy for lion 1 from the first parent, and by chance it ends up as the strategy for lion 2 in the child. We take, let's see here, we take lion 2 from the third parent, it becomes the strategy for lion 1 in the child. So we're basically taking the individuals that survived in the population and taking strategies and copying them into the child, which if you think about it seems a little bit strange. So maybe a better thing to do is restricted breeding, which means when parents are contributing genetic material to a child, like goes to like. So L1 is copied into L1 in the child. L2 from this parent goes into the child here. Lion 3 from the third parent goes into L3 here. And lion 4 from the fourth parent goes into lion 4 here. This is just showing you the copying. But remember, whenever we do an evolutionary algorithm, we do randomly modified copying. So whenever one of these subtrees is copied, we make some random mutation to it, right?
You might have already said this, but so you copy different you might copy the first line from one group.
Right, copy the strategy for lion 1 into the child. So on the right-hand side of the big arrow here, we're constructing an individual tree, and that individual tree is encoding 4 strategies, one for each of the lions. So the question in each of these 3 rows here is how to construct a new tree, a new child tree. And there's obviously different ways we can do this. Okay. So we have now 3 different ways of evolving these trees. In one, we just have a population of trees, and they just encode the same strategy for the pack or the pride, free breeding and restricted breeding. 3 different ways of evolving these things, and 3 different ways of allowing the lions to sense their environment. And we're going to do each combination. So we're going to take each perceptual ability lion and combine it with one of the 3 ways of breeding, which gives 9 different experiments. Okay, and we'll work our way through these. So we're going to do 100 runs for each of the 3 sensing capabilities and each of the 3 team construction methods. So 100 runs of each for 9 gives us 900 runs. And then we're going to do an additional 300 runs. We're going to do 100 runs with one evolved lion, 100 runs with 1 randomly moving lion. So there's really no evolution here. It's just random search. And then a final set of 100 runs with 4 randomly moving lions. So we have 12 slightly different experiments we're going to look at, and we're going to try and look at which ones produced better lions and why. Okay. The rest here details about a single evolutionary run. So a single evolutionary run, we create 500 random trees. We evolve it for 51 generations. Why 51? Because the first generation is random, and then we evolve for 50 more generations. These trees can get pretty big. They can contain up to 70 nodes, and they can have a maximum depth of 17. So we can evolve some pretty sophisticated behaviors if they're useful. And every time we're creating a new tree, sometimes we do it by crossing over genetic material from 2 trees. Most of the time we do that, and sometimes we introduce a mutation. So now we have one tree. We take that tree and we disseminate strategies into the 4 lions, place the 4 lions and the gazelle at random positions on the Serengeti donut. They each are allowed to move 15 times. And at the end of those 15 times, if there is one lion that is less than 1 unit distance away from the gazelle, it captured the gazelle, and the 4 lions get highest fitness, and here lower fitness is better. So the best you can do obviously is capture the gazelle. If the pride does not capture the gazelle, then your fitness is how close the closest lion got. Yeah, makes sense.
What if you caught the thing that was brave at the beginning and then it ran away?
Then it ran away. You got to capture it at the end.
Oh, okay.
At the 15th time step, how close is the closest lion to the gazelle? Okay. Yes?
I didn't understand, but on 100 rounds, one lion with all behavior, are there always 4 lions?
So we got 12 experiments here. In 2 of the 12 experiments, there is a single lion. Okay, I think this is a good place to pause. We'll see what evolution came up with on Thursday. You have a quiz due tonight. See you then.